break. Start by defining stoichiometry. Stoichiometry means measuring elements. It's just a big fancy word for converting between different elements. We've learned mole conversions within an element or compound, and we've learned atom and molecule conversions within an element or compound, but we haven't learned the conversion when you've got a reactant forming a product, or reactant reacting with reactant 2, how we convert between those different compounds. And that's all stoichiometry really is. On Edline, there's a flow chart that I will also hand out that goes through all of the various things that stoichiometry allows us to do. Now remember, mole conversions between moles and particles could be atoms or molecules, moles and mass were what we did during Chapter 6. So this section here was Chapter 6. We did all of these conversions. So it would be the same thing for compound B as it is for compound A. This chapter we're going to add in molarity, and we're going to add in this key piece right here, converting from compound A to compound B. We do that with the ratio from the balanced equation. So once we have a balanced equation, what we added in Chapter 7 and 8, we can put that together to do any type of conversion we want. We can go from atoms of compound A to atoms of compound B. We could go from grams of compound A to grams of compound B through this middle point. So this was Chapter 6. This was Chapters 7 and 8. Now we're going to put them all together to make Chapter 9. This is a good flowchart to remember, to try to remember the steps that you need. Every one of these arrows is a conversion factor. So if you wanted to go from mass of particles A to mass of particles B, you would need to do one step here, one step across, one step down. So 3 total conversions. So in stoichiometry, we're basically using the chemical equations that we learned how to balance and write in Chapter 7 and 8. So think about the equation 2H2 plus O2 forms 2H2O. This gives us proportional conversions between hydrogen, oxygen, and water for this reaction. And it meets the requirements of the law of conservation of mass. The key to making any conversion is to convert on common units, which is moles to moles. So in this reaction, H2 plus O2 forms H2O, or the reverse, the decomposition, 2H2O forms 2H2 plus O2. You could describe it in any of the 4 ways in the 4 rows here. 2 molecules of water decomposes to produce 2 molecules of hydrogen gas and 1 molecule of oxygen gas. We could just as easily say 2 dozen hydrogen water molecules decomposes to produce 2 dozen hydrogen molecules and 1 dozen oxygen molecules. Or we could say 2 times 6.02 times 10 to the 23rd molecules of water produces 2 times 6.02 times 10 to the 23rd molecules of hydrogen, and 1 times 6.02 times 10 to the 23rd molecules of oxygen. But the most common unit we're used to using that comes right out of that is moles. So you can think of a balanced equation as a mole ratio. 2 moles of hydrogen, or of water, producing 2 moles of hydrogen and 1 mole of oxygen. We can come up with any conversion factor we would like out of those relationships. So the conversions we're going to make are mole-to-mole conversions, and then the key one we're going to eventually get to is mass-to-mass, because we don't have in the lab something that tells us the number of moles in a sample. We have something that tells us the mass in a sample. So we're going to be able to want to convert mass to mass. We'll start with this first video with mole-to-mole conversions. So let's look at some practice problems of the mole-to-mole variety. How many moles of hydrogen gas are needed to react completely 5 moles of chlorine gas to produce hydrogen chloride gas? The first step in any one of these problems is to write the balanced equation. So hydrogen gas plus chlorine gas reacts to form hydrogen chloride gas. We need to balance this, so we need a 2 here. Now take your starting information, 5 moles of chlorine. We want to convert from moles chlorine, the thing we want to cancel, to moles of hydrogen. The numbers that go in here are the coefficients in the balanced equation, which in this case is 1 and 1. So 5 times 1 divided by 1 gives us 5 moles hydrogen. So 5 moles of chlorine react, 5 moles of hydrogen must react. Okay, try this one on your own. Press pause and then press play again when you're ready to watch my explanation. O2 gas, remember the first thing we're doing, plus H2 gas forms H2O gas. To balance this, we need a 2 here and a 2 here. So we have 4 moles hydrogen. In this case, we want to cancel hydrogen and go to oxygen. We take the numbers from the balanced equation, 1 mole O2 for every 2 moles H2, we get 2 moles of oxygen. So for 4 moles of hydrogen to react, we need 2 moles of oxygen. Okay, how many moles of calcium oxide are produced when 5 moles of calcium reacts completely with oxygen gas? So Ca plus O2 forms CaO. Calcium is plus 2, oxygen is minus 2. So 2 and a 2. We start with 5 moles calcium. Factor label method, so we want to cancel moles of calcium. We want to find moles calcium oxide. So it doesn't matter if it's reactant or product, anything in the balance equation can work here. So take the coefficients, 2 and 2. So in this case, our answer is 5 moles of calcium oxide. Okay, for the next couple of problems, for each of the following unbalanced chemical equations, calculate how many moles of each product would be produced by the complete react conversion of 0.125 moles of the first reactant. Please do this in proper dimensional analysis. So stop each of these problems, try it yourself, and then go on and look at my answer. So here we have the equation. It's not balanced, so we need to balance it first. So I'm going to put a 2 here. So I'm going to write it down below. 2 FeO plus C forms 2 Fe plus CO2. We've got 0.125 moles of FeO. We want to find the moles of each product. So I'm going to do 2 conversions here. In each case, I'm canceling moles of FeO. I want moles of Fe in the first case, moles CO2 in the second case. So each product. In this case, it's a 2 to 2 ratio. In this case, it's a 1 to 2 ratio. So in this case, we get 0.125 moles of Fe. In the second case, 0.125 divided by 2, 0.06 moles CO2. Okay, and the next one, Ki plus Cl2. So we need to write the balance equation first. Here's some review of what we just finished working on. Ki plus Cl2. This is a single replacement, so our product will be KCl and I2. So it's a 2 to 2 ratio. So we have 0.125 moles Ki. We're going to convert to each product. So moles of KCl from moles Ki. Moles of I2 from moles Ki. In this case, we have a 2-to-2 ratio, so we get 0.125 moles KCl. And in this one, we have a 1-to-2 ratio, so we get the 0.0625 moles I2. Okay, here's another one. This should stand out to us. Two compounds, one's a base, one's an acid. So we know it's an acid-base double replacement. So H2O plus Na2SO4. Balance it, we need a 2 here and a 2 here. So we got 0.125 moles NaOH moles NaOH. We want moles Na2SO4. We have a 1-to-2 ratio. 2 moles NaOH, 2 moles H2O. So we've had a lot of 2-to-1 and 2-to-2 ratios in these problems. It's just a coincidence. So we get 0.125 moles H2O. And we get 0.0625 moles Na2SO4. We're going to do one last one here. C2H2 plus O2. Recognize this as combustion, so the products are CO2 and H2O. So we have a 2 here, a 1 here. The problem is that gives us 4 oxygens, 5 oxygens, which we can't do on this side. So I need to make this a 2, a 4, and a 2, which gives me 8, 10 oxygens, so I need a 5 here. So 0.125 moles C2H2, 0.125 moles C2H2. I want to cancel moles of C2H2. I want to get moles of CO2. So this is a 4-to-2 ratio. I want to cancel moles of C2H2. I want to go to moles H2O. So in this case, I get 0.125 moles H2O. In this case, I'm going to get 0.250 moles CO2. So bring your notes on this to class with you tomorrow, and we're going to be doing a number of these type of predicting product problems, balancing equations, so that we can continue to practice those concepts and now add in